Hi, everyone. Welcome to today's workshop. We'll be starting promptly at 1 o'clock. Appreciate everyone joining early to make sure that things are working. And while we wait for the official start time, we do have a question for the group. So the opener question for today's workshop is, your manager asks why the doors to the production area keep slamming shut. What do you tell him? And you can respond either using the link that Evan's about to drop in the chat, the QR code below on your phone, or you can go to menti.com and enter the code on the screen. We're going to be using Menti a couple of times throughout this workshop, so you can just leave that open in the background as we proceed. Okay, so we're Bill joining in. As mentioned, we have a starter question for this. So your manager asks why the doors to the production area keep slamming shut. What do you tell him? Noise prevention. I like that one. Yeah. Air pressure not balanced. Huh. Okay. Go and find out why before telling them. Right? Don't make assumptions. I like that one too. So, the air pressure not balanced. I appreciate the answer of we'll go find out why before telling them, before answering the questions. But given that today's theme, the topic for today's workshop is air balance studies, um, we're thinking about that air pressure not balanced that might be causing that. So, uh, stress relief, another good one. All right. So, by the end of this workshop on air balance studies, we're hoping that you'll understand some of the fundamentals of balancing pressure in a facility, of air balancing that in a facility, being able to interpret some airflow data, diagnose imbalance issues, and identify next steps to support your air balance study if it makes sense for you to pursue one. We do have a participant workbook that contains a summary of the information that we're going to be talking about today. So the link to that is in the chat. Please click the link. It will open a read-only copy. So if you want your own, you'll just click File and Download to save your own copy, and you can follow along with that if you want. So first, we're going to talk about why air balancing matters. But before we get into that, a little preamble about what we mean by air balancing, because we want to be clear what we're talking about. And I've heard air balancing refer to different things. So on the one hand, air balancing, balancing airflow within an HVAC system, that can be done to ensure that the airflow pressure at each of the terminals aligns with the design operational requirements, making sure that that flow is balanced through the system. Another way to talk about air balancing is balancing exhaust and makeup air to reduce positive, negative pressure conditions in a facility. So in this workshop, we're going to be focusing on the latter, balancing exhaust and makeup air. So why is this important? So buildings where there is more air being exhausted than is being supplied into the building, that's going to create a negative pressure within the facility. This is actually pretty common in industrial facilities and means that air is going to be pulled into the building anywhere it can. So that negative pressure is going to be pulling air in. Conversely, when there's more supply air being brought into the building than exhaust air pushing air out, that's going to create positive pressure inside the building that pushes air out of the building wherever it can, either through doors, openings, leaks in the envelope, etc. And sometimes maintaining that positive or negative pressure is intentional. So there's situations where you want to keep contaminants out, like if you're manufacturing sensitive electronics or food and beverage or pharmaceuticals, and it's important to maintain a positive pressure because that's pushing air out. It's going to keep contaminants out of the clean areas where you don't want them. But there's other situations where you're dealing with odors, harmful chemicals, toxic fumes, and in those ones, it's important to maintain a negative pressure so that those harmful chemicals or fumes don't leak into areas where they're not supposed to. So you want that negative pressure to be drawing the air in, preventing it from escaping through into places where you don't want it. It should be noted that this differential, even in the intentional situations where you're purposely using it for these reasons, it doesn't need to be huge. So like ISO 14644, it has 9 levels of clean rooms, and the recommended pressure differential to prevent contaminants from one level getting into the next is about 5 to 20 pascals, and the people will typically design for around 10. So that's 0.02 to 0.08 inches of water column differential. So we're not talking about like a huge pressure differential. And sometimes you might be getting even more than that by accident in your facilities. For industrial facilities that don't have specific requirements around positive or negative pressure, it's often recommended to keep them slightly positive. This can help improve comfort because it helps keep temperatures more stable because you're pushing air out, but that's conditioned air. You're not drawing in cold air through drafts in the winter, so it improves comfort. It can improve indoor air quality because it limits odor and contaminant entry into the general space where people are working, helps better control ventilation, and it also helps with infiltration control. So keeping uncontrolled outdoor air coming into the facility in the summer, that can be bringing in a lot of humidity that can also impact comfort as well. So it's generally recommended for industrial facilities to keep a slightly positive pressure. And that's, a typical target I've seen is like around 0.01 to 0.03 inches of water column differential. So 2.5 to 7.5 pascals. So not big. But we often see facilities with a pretty significant negative pressure. And usually because there's a lot of exhaust for industrial processes happening, and the makeup air isn't always properly balanced. So you may unintentionally have high negative pressure, or even in some cases, if it's the other way around, unintentional high positive pressure. Balancing that out has a number of benefits for occupant comfort. They said you have more consistent temperatures, better employee satisfaction, better indoor air quality. It can improve energy efficiency. So balancing this out can prevent over ventilation or under ventilation, which wastes heating and cooling energy. It can allow fans and equipment to operate at their intended static pressure and speed, reducing electrical demand. Because if you have that negative pressure in your facility, the exhaust fans now have a greater static pressure that they're kind of fighting against. So that's going to increase energy consumption. And going through the process of air balance studies can also support data-driven control strategies like demand-based ventilation that match airflow to occupancy or production needs. It can also be important for compliance and safety, ensuring that you have the right pressurization in critical spaces like labs, clean rooms, paint booths, help maintain building codes and industrial standards for ventilation and safety. And it can also reduce risk of fume migration or exhaust backflow, protecting workers and products. So, for a paint booth, if you have an opening in your paint booth, you need to keep a capture velocity of the airflow across that opening for safety reasons so fumes don't escape into the area where there are people. If you have negative pressure in your facility, it could impact the effectiveness of that, reduce the capture velocity, allow some of those fumes to escape. So there's lots of benefits around safety, and then also equipment performance. As I mentioned, like adding unnecessary static pressure to this equipment can cause issues with maintenance, strain on fans. Having this balance can help extend equipment life, prevent premature failure, all those good things. So when we're thinking about getting these done, usually facilities will conduct air balance studies when there's significant changes to the building or the HVAC system, like new construction, major retrofits, or when recommissioning is taking place. It'll be part of that. It may also be required as part of accreditation for regulated operations. For instance, pharmaceutical facilities may need to verify the level of air changeovers and pressure differentials in their production area, that they're meeting defined standards, and that may have to be done on a certain cadence time period. But there's other reasons why you might be interested in conducting an air study. First, if you have high energy consumption, high levels of exhaust make up air, it can be a good for energy savings on that. So it can be a good way to help save energy. There can be safety concerns around that, as I mentioned, fumes, exhaust backflows. It can be related to regulatory, insurance, or audit drivers, major changes to the facility, or if there's noticeable issues or symptoms related to pressurization happening in the facility. A lot of times people think that like air balancing, it's only worthwhile doing if you have a building automation system that can control and you can adjust to address some of these issues. And that is very useful, but it can still be worth doing even if your facility has manual or standalone systems, like rooftop units, exhaust fans, VFDs that can be manually adjusted based on the findings. Or if there's like known comfort, indoor air quality, pressure issues, doing that study can help quantify that and suggest changes to address those issues, even if those changes are manual controls. And also the results from these studies can help inform future control upgrades or planning capital by identifying the biggest problem areas that you have. Sometimes we see organizations doing this just because they want baseline airflow data for use in energy audits, recommissioning, or performance tracking. But there are limitations if you don't have an automated control system. So no centralized control means adjustments have to be made locally, and verification can be slower, more labor intensive. The lack of trend data makes it harder to track long-term performance because you get that snapshot, not continuous insight. And those manual systems can drift out of balance faster, particularly when you don't have an automated system that can keep an eye on it and verify that it's still working as intended. In terms of facility size, facilities under about 25,000 square feet don't often undertake air balance studies just because it doesn't make sense for the cost. The exceptions to this is if there are safety concerns like backdrafting, or if they have particularly high process exhaust. So thinking like 7 to 10,000 CFM. Facilities in the range of 25,000 to 100,000 square feet is more that sort of threshold or trigger point where it makes sense to pay more attention to balancing your airflows, especially if you do have that high process exhaust. So thinking like greater than 15,000 CFM, if you have multiple exhaust types, multiple makeup air sources, a more complicated system. Another rule of thumb that's often used is your air changeovers. So if you have more than 1.5 air changeovers per hour, there's probably a lot of energy going into that. So it becomes more recommended to undertake air balance studies if you are experiencing some of these symptoms. And part of the reason for that is that, as a general rule of thumb, fixing pressure imbalance can reduce HVAC costs by 15 to 30%. Of course, this isn't guaranteed. And often when it comes to air balance studies, the primary driver is safety, air quality, comfort. But again, depending on your energy use and the size of your facility, there can be significant energy savings as part of that. The symptoms to look out for that can indicate that there might be a problem are hot, cold complaints across different areas, zones of your facility, because those pressure differentials could be drawing in cold air from outside or hot air from different areas. Drafts, unusual noise, vibrations in ductwork. If there's indoor air quality issues, even though maybe you suspect you should have enough exhaust or fresh air to deal with it. If there's pressure complaints, so doors being hard to open, slamming shut, odors spreading in the facility. If there's high energy use from fans, or trending data shows that your fans are running harder than they should be, your exhaust or ventilation fans. Also, if you have recurring HVAC service calls for similar issues over and over, that could indicate that there's additional unnecessary stress on some of those components of your systems. So all these can lead to give clues that there is a pressure problem, and it might be worthwhile undertaking an air balance study. If anyone has any questions or comments or experiences they'd like to share, please do so in the chat as we're going through this. So what is an air balance study? So at the beginning, we talked that there's two types. We're going to call them type 1 and type 2. These are not official names, but just so we can distinguish them. The first type is that duct terminal flow balancing. So that focuses on balancing airflow within a duct system so that each diffuser grill terminal receives the designed airflow and pressure. It can solve issues with uneven temperatures between zones, some diffusers delivering too much air, some not enough, and verifying that the system performs as designed, particularly after installation or modification. And typically this leads to adjustments in dampers within the system, fan speeds, or distribution within the duct network, often conducted by testing, adjusting, balancing professionals. And one point on this is that it's very useful to ensure that your air flow systems are working as intended, as designed, but this type of study isn't going to be addressing the building pressurization issues. This duct system could be perfectly balanced at every diffuser and still be leading to negative or positive building pressure because of other aspects or other systems within your building. The second type that we're focusing on today focuses on looking at that total supply, exhaust, makeup air, and how that can be balanced to control the pressurization. So this solves for odors, fumes, dust moving between spaces, doors being difficult to open or close, pressure alarms, unstable system operation, and it looks more at things like total air supply versus total exhaust, makeup air availability, pathways, the system response under real operating conditions, and this is specifically meant to address those pressure problems, not diffuser problems. So those are two separate things to keep in mind in what you're looking for. Thinking about what problem are you trying to solve? Are those issues related to HVAC systems not operating as designed? If that's the case, you're probably looking towards that first type. But if it's broader issues related to facility or places within the facility and the pressurization of those, that's when we're looking at the second type of study that we're talking about today. And what's involved in these air balance studies? So we're going to do a quick overview of this before getting into more detail. But essentially, there's three main steps in the study itself. And this is sort of when you're looking at the data, what's happening in your facility, getting that understanding. There's a desk evaluation, visual inspection, and measurements. The desk inspection or desk evaluation, it's really about you're collecting information, records, information about equipment. So for exhaust systems, you're looking at the process exhaust, dust collectors, fume hoods, general exhaust, bathrooms, boiler, or other combustion equipment. And for the makeup air units, you're looking at dedicated makeup air units, outdoor air dampers on air handling units, door louvers, infiltration through the envelope. And you're going to be collecting mechanical drawings, airflow schedules, equipment specifications, finding out total exhaust and supply capabilities, ratings on there. The goal of this is to identify all of those exhaust and makeup air sources. So starting to build that inventory of everything that's bringing air into the building or sending air out of the building, using those ratings to calculate that net airflow, and at that high level, just based on nameplate, determine if you have enough makeup air unit capacity, if that's sized correctly for the exhaust, or vice versa, right? So like, do these balance out just at the nameplate level, or are there significant differences? And this can happen, facilities expand, you bring in new pieces of equipment, add new exhaust to treat for those processes, and sometimes facilities don't always add additional makeup air units for that, so you can get this imbalance even just on paper. So it's good to sort of understand that. Next part is the visual inspection. So this is, you want to identify those symptoms that we talked about. So doing a walkthrough, talking to people, operators, maintenance staff, production supervisors, looking at your air handling units or your makeup air units, confirming that units are bringing in outdoor air or recirculating air. Sometimes units labeled makeup air units might actually be recirculating interior air, or air handling units that might be assumed to be recirculating could be bringing in outdoor air as well. So, that visual inspection, what's actually happening, looking at maintenance issues, are fans running, are filters clean, dampers operational, is exhaust only running when it's needed during operational hours, are louvers blocked or closed, is the exhaust makeup air units, are they running when expected? Looking at the building envelope, gaps around exterior doors, missing damaged door seals, damaged dock seals and loading docks, unsealed wall or roof penetrations, open louvers or broken windows. So, where can air come in and out of the envelope in an unintended manner? And lastly, doing that visual inspection of the control systems, whether that is a BAS or whether it's local controls. You want to be looking at, our interlocks between makeup air and exhaust enabled? Are they working? Are fans following correct schedules? Are building pressure sensors calibrated and functional? Are economizers working as intended? Are damper positions, are those accurate? Appropriate VFD set points, alarms are working in place, are as intended on like burner lockout, damper faults, that sort of stuff. Are all those alarms clear? Is the outdoor air minimum flow set correctly and not too low? So you want to check all of those. The goal with the visual inspection here is to start zeroing in on where issues might be occurring and what those causes might be, determining if the envelope and systems are working as intended, and to try to identify some easy to fix maintenance issues if those are present. The next part of this then is measurement. So where you're wanting to collect pressure difference, getting some data on what is the pressure difference between inside the facility, outside the facility, but also between zones. Because, if there's an office area, production facility, paint area, warehouse, there may be separations between zones in your facility, and getting actual data around what are the pressure differentials there can help zero in on what are the issues. You also want to collect data on airflow. So what is the airflow from, like, that the exhaust systems are ejecting from the makeup sources, and then collecting data on actual runtime and operating hours. So when is the equipment running? How does that line up with production, with operations as well? And the goals of the measurements here are really to sort of quantify that pressure imbalance relative to the target, whether it's intentional or just looking at that slightly positive, and then to compare design. So what all the stuff you got on that bench evaluation or the desk evaluation up front, all the nameplate stuff, the facility schematics, that how does that compare to actual performance and actual operations? So you have the nameplate values, you have those layouts. Do they match up? There's often, someone moved a duct to serve a new piece of equipment, and that wasn't reflected in the site drawings. So the whole makeup air sources have sort of shifted over time. So you want to do that sort of verification of, if we have, does the measured data align with assumptions around how things are running? How you can take measurements. A bolometer is an air balancing instrument. It has a hood, an array of pitot tubes and sensors in the base there. This is used to directly read airflow rates from intakes, outflows, ceiling, wall, floor diffusers. Manometers are a really useful tool for balancing the pressure. They measure pressure differential between two places, whether that's, you know, across ducts, across like before, after a filter within an airflow system, or even between like inside, outside, between one room, another room as well. So they're really useful for pressure differentials. And anemometers are also a really important tool to have in your toolkit for measuring airflow velocity, particularly at those like capture points and stuff to make sure that you are having the required airflow across those different openings as well. So these are often used in the air balance studies. And then the results of the air balance studies, you often get that inventory of equipment. Where is all the air coming into the facility? What's all the equipment that's exhausting it? And that should show, nameplate, actual flow, condition of all the pieces of equipment. So a full inventory. They'll provide a mass balance analysis, so showing airflow in and out of different areas in your facility, indicating which makeup air units should be operating in correlation with specific exhaust units to balance that mass flow within a specific area. This is really useful to indicate those imbalances that are happening by zone. Air balance study should also be pointing to some root causes of that. So a summary of what is contributing to that excess positive or negative pressure. And lastly, some recommendations around corrective actions that can be taken to address and maintain appropriate pressurization. So that's sort of what's included, but we're going to take a little bit of a closer look at the air study process and what's included in that audit. So here's some of the main work that goes into conducting that to give you a bit of a better familiarity with what's going to be involved. So the first one is building that inventory. So we mentioned that before. On the exhaust side, obviously you're looking for those roof exhaust fans, process exhaust, dust collectors, fume hoods, paint booths, welding booths, washroom exhaust. But you also want to capture like any oven, dryer, kiln, or other combustion related exhaust. So within that equipment, they're going to have some exhaust to expel the combustion products. So you want to make sure that that's being captured in that inventory as well. Also, any always on general exhaust that is often overlooked or people forget about in facilities. So sometimes there's just like always an exhaust fan running in certain areas. On the supply side, again, you want to make sure you're capturing all the makeup air units, obviously, but also, rooftop units or air handling units that have an outdoor air intake component. Not their total supply, but you want to know that outside air component. If you have any dedicated outdoor air systems, but also some things that are commonly missed, things like compressed air. That might be bringing air in from outside the facility, purge air, relief air paths, depending on how large a role or the size of these systems in your facility, those can have a material impact on that air supply side of things. That next step of conducting the mass balance is where you compile all your airflow measurements. So you want to be comparing that total exhaust to total outdoor air supply. You want to break it down by zone within the facility, as mentioned before, but also you want to note the impact of changes in operations. So different shifts, different temperatures, seasons outdoors, when like loading bay doors are open versus when they're closed, because those can all impact airflow. They can all impact pressurization within the facility. And you want to get an understanding of what does that mass balance look like under different operating conditions, not just one, because it's going to be a dynamic system, right? As things change within your facility, that pressure differential, that pressure balancing is going to change with that, and you want to make sure you have the full understanding of it. With that information, that's when you want to start confirming what's driving that imbalance. So common causes of this are, the outdoor air dampers aren't working as intended. There might be airflow blockages, clogged filters, other things restricting airflow. There might just be insufficient makeup air or exhaust happening. As I mentioned, things change in facilities, and even if it was balanced at design, as equipment was added or removed, it may no longer be balanced in that way. Fans might be running above design. If a VFD is malfunctioning or no longer connected or operating properly, that fan might be running full speed when it shouldn't be or wasn't previously. Another common cause is exhaust or makeup units running when they're not needed. So if there isn't the need for the exhaust, but you still have a lot of exhaust fans running, that can cause challenges as well. So these are all common issues with that. Once you've identified these, one thing that's really important to do is to test the worst case condition. So as I mentioned, you want to start collecting data under different operating conditions, but in doing so, it's really good to think about what are those worst case conditions where either your exhaust is really high and supply is really low, or vice versa. Your supply is really high, your exhaust is really low, and test for those. So this could be things like, all the processes are on and all the bay doors and exterior doors are closed. So there's not a lot of air coming in, but there's a lot of air going out. Looking at minimum ventilation mode in winter, where you're bringing in only the minimum outdoor air that's needed, but you still have your exhaust on at full capacity. Warm weather, when economizers are active and bringing in more air, or when there's things like shift changes, when doors open and the people traffic spikes throughout the facility. And it's really important to consider these worst case conditions and test for those in the study, because the last thing you want to do is go through the study and assess the problems and make those changes based on typical operating conditions, but then still have problems when these kind of worst case scenarios arise. So hopefully you've done all that. Once you've done all that and have a good sense of what's happening and have identified those solutions, you want to prioritize the fixes. And there is a good order to do this in. First, addressing those maintenance issues, things like outdoor air dampers. Are they open to the commanded position or what the control says it should be? Looking at the intake filters, screens, coils, make sure they're not choking flow. Relief dampers can actually relieve pressure, and BAS points are scaled correctly. Sensors are working, not installed in turbulent locations, giving poor ratings, that sort of stuff. These are typically the lower cost issues to fix and can make significant difference. So it's good to start with those. Next, you're identifying your pressure targets by zone. If you want slightly positive overall, is sort of the general recommendation. You'll usually want loading docks, neutral or slightly negative pressure to the rest of the facility, so that odors or truck fumes aren't coming into the rest of the plant, and that dirty process areas are negative pressure relative to cleaner areas, so that it's not pushing the dust or the fumes or exhaust into those other areas. So having those targeted on there. And then the next thing is looking at providing additional makeup air to match exhaust, or vice versa if it's balanced the other way around. Because if your exhaust is truly higher than your outdoor air supply is capable of meeting, there's a couple of levers that you can use. So this is a really common situation where there's a lot more exhaust happening than makeup air units supplying air. You can add more outdoor air supply. So, add more makeup air units, increase outdoor air percentage. You can reduce your exhaust if this is allowable by your processes. Things like shutting down exhaust when not needed, installing demand control VFDs on the exhaust units. To help balance some of the energy considerations, you can add heat recovery or smarter scheduling to minimize the energy impact of high air changeovers. And another thing on here, if it's not matching, is zone dampers. So controlling flow between zones can help ensure process areas with the high exhaust get priority air supply on there. So, in most industrial sites with heavy exhaust, there's dedicated makeup air units. Ideally, those should be sized for exhaust. But again, sometimes things get moved around, and that makeup air unit may be supplying a lot of that air to a region in your facility that no longer has high exhaust levels if things have moved around. So using dampers or redirecting flow to help make sure that that's taking place. The next priority for the fixes is implementing controls. So an example of this is interlocks between exhaust and makeup air units and connecting those to processes so that during operation, they're locked together. So if exhaust comes on, equivalent makeup air unit capacity comes online and they turn off when they're not needed. Controls can also control like fan speed, dampers, relief controls based on the building pressure set point. So in a BAS, you may have like, hey, we don't want to exceed, a +5 Pascal differential, and it'll bring in more air if it more exhaust or control the input and output of the air if that threshold is exceeded. So that can be really useful, but an important thing to remember on that is making sure you have some guardrails on to account for things like, loading bay door activity. If the doors are open and not wanting to exceed a threshold because of that impact, or making sure that you're not putting things at risk of freezing by bringing a whole lot of outdoor air to address a negative pressure situation, or making sure you're still meeting minimum outdoor air requirements, even if that does result in positive pressure or things like that. And number 5, addressing leakage and big door impacts. Now, this one should be done last because if you start fixing these leaks and these infiltration issues before addressing the air balance issues, then that can make the problem even worse because you're restricting that flow and even like increasing that pressure differential as a result. But this can include things like improving seals, using air curtains on loading bay doors and things. May also consider like a local makeup air unit in loading bays to reduce air infiltration and maintain comfort there. Some common mistakes that happen in these studies is, balancing to outdated layouts or equipment. So you want to make sure that you verify all as-built conditions, confirm current equipment configuration before taking any measurements. Another common issue is applying sort of stopgap fixes instead of addressing root causes, like wedging dampers open instead of figuring out why they aren't operating correctly. So in this thing, make sure you measure the airflow first and identify the root cause of the imbalance, and then make those adjustments based on the data and not just sort of, it's negative pressure, let's jam a damper open to address that. Another issue is ignoring return exhaust airflow space pressurization. So make sure to include your supply, return, exhaust pressure relationships in every assessment. Don't measure one in isolation. Often, it's not fully documented in terms of the baseline and final conditions. So it's really important to record your airflow, pressure, damper position, equipment status before and after any adjustments to ensure repeatability. Because, if a year or two later, those pressure issues start popping up again, you can refer back to that before after state, see if things are reverted. It can sort of shortcut any corrections later on. Another common issue is skipping verification after adjustments. So always make sure to remeasure or verify system performance after each adjustment to confirm that balance is achieved, confirm things are operating as intended, and making sure that that is taking place. And having that confirmation place is very important. And lastly, common error is conducting the balance only at one set of operating conditions. So I mentioned before the importance of testing that airflow under multiple load scenarios, shift changes, different seasons when different equipment's running, to make sure you do have that dynamic stability. So as the conditions in your facility change, it's able to adapt with those to maintain, the comfort and proper balance of pressure, regardless of operating condition. So I know I've been talking for a while here. We're going to go through just a couple of short scenarios and get your input. So if you can go back, if you can open up the Menti question again, we're going to be going back to that in just a second. So be ready for that. Be ready to participate. And if you're new, the link is in the chat. So in our first scenario, Energy Manager notices some systems of negative facility pressure across the facility. Team conducts their own air balance audit. They dig out the old building design drawings, use those and equipment specs to map out the exhaust, makeup air ratings across different zones. They've identified where the imbalance exists, and they see where the mass balance indicates the need for a new makeup air unit, and they install a new makeup air unit. Unfortunately, it seems it's made the pressure differential even greater between those zones, even greater. So it didn't solve the problem, it actually made the problem worse. So, oops, I'm just going to go back to, here we go. Okay, the question in the Menti should be up now. What went wrong? And there's 4 options to see there. So what do you think went wrong? They did that study, they looked at all the equipment drawings and specs, mapped out how much air was coming in and going out in different zones, installed a new makeup air unit, and it made the problem worse. So what did they do wrong? All right. Yeah, so some saying they didn't buy the right sized makeup air unit. That could be correct on there. They didn't document your findings. That's also correct. There's good practice. They didn't do that, but I think what this one's pointing to is they balanced based on old system designs, and they didn't verify actual airflows. So these first 2 ones where they did that desk evaluation, they looked at the facility drawings, they looked at the spec sheets for their equipment, and came to their conclusions based on that without verifying on the ground what was actually happening. So really important step to not just trust what is on paper. Okay, so the follow-up to that, what should they have done differently before starting the balancing, before implementing solutions? I'll give just a minute here for people to type in some answers. So they just based it off of the drawings and equipment specs and ended up making the problem worse. What should they have done differently? Obtain current drawings, yeah. Like make sure they're up to date, verify the data, get the most recent drawings. Sometimes I know these things are hard to find in facilities, but getting out there, sort of like conducting that new study, real-time data, using data, getting out into the facility, verifying that the equipment is there, installed as per drawing or if there are any variations. Measure the airflow at the equipment level. Talk to facility management. Excellent. These are all great tips and suggestions. All right, we've got our next scenario. Scenario B. So your team receives complaints about drafts and doors slamming shut in January, indicating negative pressure in the facility. You take this to management, you get approval to conduct a study, find a consultant. By the time all that's done, that takes place in April. The study review the drawings, equipment specifications. They do measure flow, map out exhaust and supply. Range of issues are identified, from broken dampers to control issues, which are then addressed through June and August. But 6 months later, the team starts getting the same complaints about drafts and doors slamming. So in this one, bring up the Menti here. What went wrong in this scenario? So scenario B, they went through that. They used the drawings. They actually got measurements this time. Implemented all the fixes, but then after 6 months, they were starting to get the same complaints that they had before. All right, so we've got some suggestions coming in here. We've got a couple answers on, they didn't confirm the drivers of imbalance. That's possible. There were things like the broken dampers and stuff like that. There could have been other things that were going on that wasn't the real problem. But it looks like most of the people are answering here that they didn't test under the worst case conditions. So the situation in January, when they were getting the complaints, outdoor air percentages and different things like that can change. They might be minimizing outdoor air, but still having a lot of exhaust happening. By the time they got around to doing the study, it was in the spring, and then they implemented stuff in the summer. So it could be that, their operations in January in the winter represent a kind of worst case scenario in terms of imbalance that the study didn't pick up on and that the solution didn't address. Great comment from Faisal in the chat there about, the seasonal adjustments are required. If they didn't take this into account in the study, they may not have realized that they have to make seasonal adjustments to balance this and to keep that balance happening. So even though those issues were resolved under some conditions, there were still conditions where it wasn't. So in this case, what should they have done differently? Oh, wait, I think some of these answers got put in from the beginning question. So we'll ignore those first three. But in this situation where issue is addressed in January, study done in April, fixes in the summer, what could they have done differently to try to fully address the problem? Yeah, look at different times of the year, seasonal performance testing. They could have done some testing, sort of like setting the conditions of the system to what it is at different seasons. So if they, if their dampers are or their outdoor air percentage changes throughout the year, do some tests around that. Good point about identifying when they were seeing the issues, really taking that into account and not assuming that they were just consistent, that they might be time dependent. Yeah, verifying system things such as economizer operation might be excellent. All right, so these are all great tips on how they could have avoided that challenge. Excellent. All right, you all know what's going on here with these studies. So the next thing we're going to look at is less around like what's being done in the study, but how you and your facility as an energy manager might go about planning one. So we have 6 steps here, going from you're seeing some of those symptoms all the way to full implementation of solutions. We're going to go through those in a bit of detail now. So the first step is confirming those symptoms and risks. So, verifying those reported systems, the doors, drafts, dust, odors, complaints you're hearing, things like that. Not just what it is, but where it's happening in the facility. At this point, you also want to assess if there's any potential risks or safety concerns. So, as mentioned before, those safety issues are often some of the biggest drivers for doing these types of studies. So, if you're starting to see some symptoms of negative or positive pressure, you want to assess if there's any safety concerns. So, combustion concerns. Uh, could there be a risk of combustion products not being fully exhausted? Um, is there a potential for backdrafts? Are there air quality issues? Are there regulatory issues? Do you need to maintain certain pressure differentials, and could that be put at risk? If it's just we think we can save energy, that's a great benefit, but it's not necessarily a risk. Where if there are actual health or regulatory risks, that can make it a really big priority. So it's important to understand that and check that. Then you want to start looking at the scope and intent. So are you looking to do this for your whole building, just one zone or one area of the building? And what are you trying to achieve with this? Are there specific target pressures that you want to achieve? Are you doing this to save energy? Are you doing this to minimize some of those symptoms that have been showing up in your facility? What are you trying to get out of this? The next step is to define your design requirements and constraints. So, what are the required exhaust capture and transport needs? So, like if you have that paint booth, what is the minimum capture velocity of the airflow across any openings that you need to have? What is the required air changeover rate for your facility, for your operations? Depending on what you're doing in your facilities, these might be prescribed by industry standards or regulations. Are there different specific pressure requirements? Like, do you have clean rooms in your facilities that have specific pressurization requirements that need to be met? And what is your target pressure differential? So again, this might be specified by industry standards depending on what you're doing, or it might just be, we want that generally slightly positive, and some areas we want slightly negative. But actually defining that, writing that down, because that'll help inform the next steps, which is choosing whether you do it yourself or hire a consultant. So there's no hard rule for this. Our recommendation, or what we often see people in facilities doing, is they'll go the DIY route if their systems are relatively simple, or they have access to a building automation system that can provide trend data and easy controls and seeing how things are working and balancing, or if they have internal capabilities to measure or do the study. And that includes both like skill and knowledge, but also the tools to do so. Like if they have those different meters that we talked about earlier. We often see organizations engaging a consultant if their systems are more complex. So if there's multiple interacting systems or equipment, if like safety critical exhaust is important, or if there's combustion issues. So once those health and safety risks start popping up, you may want to get the knowledgeable consultant in to make sure that those are being addressed properly. Or also if they just don't have access to measurement equipment or those internal capabilities to do this kind of work. And then the execute study, which we covered in detail earlier: gather information, identify root causes, develop an action plan. And then, once all that work's done, you want to implement it and verify the results and lock in those changes. So, that should be fix maintenance issues, add any makeup air capacity or reduce exhaust as needed, add controls or refine your controls, then repeat your test to verify that the issue has been addressed, again, under different conditions. Make sure you document and store all of these results for future reference. And make sure, and this last one is really important, we haven't talked about it yet, is implement procedures or regular tests to ensure that these solutions stick. So whether that's, BAS alarms or checks or regular, maintenance checklists, preventative maintenance on some of those critical systems for it, making sure that all of these things that are being implemented to make sure your pressure is balanced are staying in place and that they aren't falling behind again. Some tips on engaging a consultant, things to look for, engaging consultants that are professional engineers, mechanical engineers, especially if you think makeup units are undersized or missing, or if safety issues are involved, because they're better positioned to evaluate code compliance, modify systems, stamp drawings if needed. You want to make sure that you are getting a consultant that has experience with industrial systems. So negative pressure in these facilities is usually caused by unaccounted for or unnecessary exhaust, and not necessarily that HVAC system imbalance that we were talking about before. So you want to make sure that the consultant does have experience with industrial process exhaust systems, because that's going to play a really big role in it, or most likely. You can look for certified professionals. So testing, adjusting balance, tab professionals. They're very well equipped to measure actual airflow, perform measure mapping, that mass balance across different areas. There's different credentials like AABC, NEBB, TABB that you can look for. Things to avoid. Try to avoid controls vendors acting alone. It might be a control problem. It might be something else. Equipment sales representatives that are interested in selling a new makeup air unit as opposed to addressing your root cause. And also, I would suggest avoiding HVAC contractors without any engineering staff or industrial process exhaust experience, as we mentioned, the importance of those as well. Now, what I'd like to do is walk through a real world example of those steps, those process steps that we just talked about. Last year, Craig Carruthers from Prestran Industries joined Save on Energy for a fireside chat talking about a BAS implementation project that they did. If you missed that, the link from it has just been pasted in the chat. So I highly recommend saving that link for later and going to watch that. It's a really interesting and great description of that project. But part of that, an air balance study played a big role in that process of their overall BAS implementation project. So I wanted to focus on that, use that as an example to illustrate this process that we just went through. That first step of confirming the symptoms and risks. So in Craig's facility, they've got a lot of exhaust, weld booths and different industrial processes are happening. So high CFM air usage, high air changes per hour as a result of that. And because of that, very high HVAC energy costs. So natural gas in particular, but also electricity through the fans and everything else. They had poor controls and coordination between exhaust and supply. So they had many different exhaust units, many different air supply units happening throughout the facility, and very poor coordination between those. That was leading to a lot of negative pressure symptoms in their facility. So they were experiencing those symptoms. Saw lots of unnecessary fans running, and because of the negative pressure situation that was happening in here, it wasn't verified, but they were worried about potential carbon monoxide risks from direct fired makeup air units, where those combustion products might not be exhausted in the way that they should. So when they defined that scope and the intent, they wanted to cover the whole building. One of their goals was to reduce unnecessary exhaust and makeup air to address those potential safety risks and also to save energy because and reduce natural gas because they know they were using a lot of that. They saw that opportunity. The other intent of this study was to support their BAS implementation. So they knew that for the BAS, they were going to have to, do that equipment inventory, map things out, figure out how things should be controlled. And they saw this air balance study as being really useful to inform and facilitate the BAS implementation. When they looked at their design requirements, constraints, and started defining those, they did have specific requirements for their weld booths. So both for air changeovers in those areas, but also airflow capture at the booths. And they had facility design requirements as well. So they gathered that information and they specified what those requirements were. And then it came time to choose whether to do it themselves or hire a consultant. And in this case, it wasn't necessarily a simple system. Like I said, they had a lot of points of exhaust, a lot of different points of makeup air. So it was a bit more complex. But Craig, the energy manager there, did have an HVAC background. And as a result of that, did also have access to the measurement equipment. So even though it was maybe a little bit of a more complicated situation, they had that internal capabilities to undertake the study. Conducting the study, this one, Craig said it was completed over a couple of months, gathered equipment ratings, actual exhaust makeup flow to compare actual to design, collected and developed a lot of documentation around this, which is really important because of that BAS piece. Mapped out all of the building exhaust fans, process exhaust fans, and changed the nomenclature to reflect this. So this was a really important point, particularly thinking about that BAS. So when they were going through this, when they were mapping everything out, doing those design flows, they wanted to make sure that the nomenclature, how things were labeled in documentation was really clear what they were for. So implemented a consistent, clear naming framework for all of the different exhaust and supply ones to make sure things that like a building exhaust fan was easily distinguishable from a process exhaust fan. So that really fed into that intent around informing the BAS. And that mapping was a really involved process. I think Craig said he spent a week on the roof, like mapping out all the different exhaust and makeup air units and air handling units and rooftop units that were up there. So it was a process to do that. But mapping out all of that exhaust makeup supply, they also map that out tied to specific processes and equipment to both understand the current state, but also create the desired end state. Again, with that BAS in mind, those automated controls in mind, they wanted to be able to say, okay, if this weld booth is operational, this exhaust fan needs to be working. And if this exhaust fan is on, this makeup air unit needs to be on to counter that, or this combination of supply under different conditions. So that mapping out of the desired end state of how it would balance supply and exhaust under different conditions was a really important piece of the study and really valuable for informing the BAS operation. And then step 6, the implement, verify, lock in. So with a BAS, bringing in the BAS, they were able to implement cascading interlocks. So they had it set up so this weld booth turns on, the exhaust turns on, the associated makeup air units turn on. And that all happens automatically. The exhaust booth turns off, the weld booth turns off, the exhaust fan turns off, the makeup air unit turns off or ramps down appropriately. So they had those controls in place, which was really helpful in both eliminating the negative pressure situation, but also in terms of energy savings, because limiting how much exhaust they were using and only using that when it was needed meant they could reduce their makeup air overall to only needing to bring in and heat what was needed. And I think he said it was like a 40% reduction in like natural gas reduction, just as a result of that. The BAS also monitors the overall pressure balance and adds makeup supply or exhaust as needed. So they have all these interlocks in place, but they're also, it's like, okay, if the building is becoming negative pressure, then they'll turn on more makeup air supply to address that automatically. And then once those controls were in place and they had gotten the pressure balance under control, then they started looking at reducing leaks, air curtains, improving building envelope, that sort of stuff. Another interesting piece that they put in terms of like locking in these changes and savings is they implemented a system of escalating alerts. So, for instance, if a loading bay door was left open longer than it should be, then the person in the loading bay was notified, and if it was left open another hour or so, then the shift supervisor was notified. And if it was left open even longer after a certain threshold, the plant manager was notified, which was really good in terms of an energy saving measure and maintaining the pressure balance in the facility, because no one wants to be the reason why the plant manager gets notified of something. So it really helped people stay on top of things. And lastly, using that BAS to monitor performance over time, making sure these systems were still in place, operating as needed. So very good to make sure that these benefits are there, that they aren't reverting to a previous state, or that the previous issues aren't coming back. So a really solid implementation with that. So right now I want to take just a couple of minutes. So we've gone through this. Here's those 6 steps again. Confirm symptoms and risk, define that scope and intent, define your requirements and constraints, choose whether it's DIY or consultant, conduct that study, verify or implement, verify, and lock in. There is a one-page summary of this, sort of a template in the participant workbook for you to use. I want to take a minute here just of, does anyone have any questions about what any of these steps would look like in your facility? So are you not sure what would be relevant for your particular situation, and have questions about what any of these different steps or anything we've talked about might look like within your facility? And also, if anyone has done this or gone through this, experienced this, and has any personal insights to share with the group, I'd love to hear that as well. Oh, wait, I do see a Q&A up here that I missed. Just gonna check that out. Oh, no posts yet. Okay, I'm going to move on. If there is any questions or experiences you would like to share, please do raise your hand or just type them in the chat, and we can address them there, but that would be great. So based on that, oh, mics are muted for everyone. Oh, thanks for that heads up, Jeremy. Evan, are we able to change that?
Taking a look right now. Give me one quick second.
Yeah, sorry about that. Good to know. So while we look into that, I didn't realize that setting was on there. Because the mic's muted, if anyone does have any questions or wants to share their experiences, please do type in the chat, and we'll take just a minute here in case anyone is busy typing there.
I did also just allow mic access for all participants. So if you want to come off mute and discuss, that's perfectly fine too.
Great. Thanks, Evan. Okay. So that's addressed. if there's anything you want to share, raise your hand, type in chat, come off mute and speak. That would be great. Jeremy.
Hi there. Real quick, you mentioned that there was a participant file that was shared. I didn't get that in my emails. If I could request that, that'd be fantastic.
Okay. Evan's going to drop the link to it in the chat now. It was shared at the beginning, but if anyone joined later, they would have missed that. So you can click that and then just file, download a copy to your own computer.
Awesome. Thanks so much.
Great. Okay. So now I'd like to hear, what's one specific action based on today, if you're thinking about conducting an air balance study, if you're sort of already considering one or not sure if it's needed. I'm curious, I'd like to hear, based on what we talked about today, just in the chat, or if you want to come off mute to share, what's one specific action that you're going to take in the next month or so to either investigate or address some of these issues or implement some changes related to air balance studies and improving pressure issues within facilities. I appreciate people sharing that. It's always great to hear what the next steps or those key takeaways are. So I'm going to pause just for a minute here for that. All right, compile noted issues. Okay, so things have been coming up and have been mentioned and stuff like that to sort of point to an issue, but starting to compile those and defining that scope to address them. Great, thanks, Joe. All right. And Adam's going to use this to inform the scope of work for upcoming TAB project. Great. All right. Thanks, Joe and Adam. Still love to hear others if you're in the process of typing or want to share that. We did wrap up a little bit early today, so that's great. We can stick around if anyone does have any further questions. A couple of things on the wrap up. The Energy Managers Playbook Season 1 wrapped up this summer. There is Season 2 coming out. If you haven't heard it yet, the link to it's in the chat. Please check it out. In addition, we're looking for guests, both for Season 2 of the Playbook, but also other things. Like we have fireside chats where we feature specific projects from idea through to results, kind of like a live case study. Like Craig did one of those earlier. Back in December, we had Tony Campbell from Landmark Cinemas talking about their laser projector retrofit project, which was really cool. And if you missed it, you can find it on Save on Energy's YouTube channel. And if you do have a story that you want to share, please reach out to me. Whether that's an energy management success in your organization or a specific project. As I mentioned, we have a few ways to share these with the communities to promote some of the great work that you're doing within your organizations. Evan did put in the chat a little message about that with my email. It's just j@goldfin.ca. But if you do have any stories you'd like to share, please get in touch with me. We'd love to help promote some of the great work that's happening in Ontario facilities. We do also have an energy management community that I've recognized some familiar names from. It's free to join, to register. You get access to an online energy management learning platform with online courses, resources, a discussion forum with other energy managers in it. You also get invites to monthly discussion groups and other opportunities as well. So that's really focused on the community. And lastly, we have additional resources, as always, with the Save on Energy webinars like this. There is post-webinar support available if you have any follow-up questions or want to talk to someone about applying anything we discussed in today's workshop. So the link to that is in the chat now. And there's also other things. You can sign up for our monthly bulletin to get updates on upcoming training. There's the live training calendar and Save on Energy's training and support websites. These are all really great resources for industrial facilities, for others as well. So that wraps it up. A reminder for those. Again, thanks everyone for joining today. I saw Jeremy's comment around next steps. Having an energy committee meeting, sharing this framework approach with them will be the next step on that. So thanks everyone for taking the time to join today. Hopefully you got something out of this. As I mentioned, we did finish a little bit early, so if anyone has any questions or would like to stick around, you're welcome to. Otherwise, have a great rest of the week, and we'll see you at the next one.